Okay,
Okay.
today we are happy to welcome Francesco Mele here. Francesco is final year PhD student at SNS Pisa, and he will be joining Caltech as a postdoc researcher this fall. So his research interest spans quantum Shannon theory, CB systems, and quantum learning theory. And today he will give lecture titled Tomography of Energy Constraint and Bosonic Gaussian State. And yeah.
Thank you so much, Junzio, for uh, organizing these lectures, for inviting me on this interesting topic. Um, okay, so please feel free to interrupt me whenever you don't understand something. And yeah, I, so I will start by uh, defining the problem of quantum state tomography. Then I will talk about the basics of CV systems. And then I will talk about quantum state tomography um, of CV systems. So, and this part is divided in two parts. The first part is on energy constraints states. And the second part is on Gaussian states. So I will keep the presentation very intuitive, and I'd like to deliver just the rough intuitions of the idea, and for the details, I will refer to the links that Junzeo put on the website of this course. And yeah, okay, as I told you, feel free to interrupt me. And if you want to um, contact me afterwards to ask questions or curiosity, please write me an email to this address, francesco.mele at sns. So, okay. Um, okay, so let's start with the concept of quantum state tomography. So basically, quantum state tomography means that is the task of learning an unknown quantum states. So basically, you can imagine that you have an unknown quantum state rho, and you want to perform measurements on it to understand what this state actually is. So um, since quantum mechanics is probabilistic, outcomes are probabilistic, you cannot solve this task with just one copy of this state. But you can imagine that in a lot of practical scenarios, you have, for example, a source of quantum state, an experiment that you can run many times. So in many practical situations, you can have many copies of your quantum state, so rho tensor n. And by measuring these copies of your unknown quantum state, you want to output an estimator rho tilde that is basically the goal is that it is a good approximation of the unknown quantum state rho. So this measurement is referred to as tomography algorithm. And okay, so roughly speaking, the problem of quantum state tomography is this one. And so rho tilde is like a classical description of a quantum state, meaning that you want to store this classical description on a classical computer. And so let's let's formally define what is this condition about. So we want first to make rigorous what does it mean approximation. What does it mean that rho tilde is close to rho, is approximately rho? Okay, we want to define an error, epsilon, larger than zero. And so how to quantify this error? Okay, quantum states are matrices. You can define multiple matrices between multiple notional distances between quantum states. But there is one notion of distance that is that has a very strong operational meaning in quantum information theory. This distance is known as trace distance. The trace distance um, is known as the measure of distance between quantum states that has the most operationally meaningful physically, let's say, it has the strongest physical meaning. And this is captured by the so-called Olevo-Elstrom theorem. Um, the operational meaning of the trace distance. So the trace distance is defined as, in terms of the so-called trace norm, as rho minus rho tilde. This is denoted the trace distance, and the format can be written in this way. The trace norm is like trace of rho minus rho tilde, where this is the absolute value of the operator. So this is the definition of the trace distance. And what we want to require by our algorithm is that the estimator rho tilde is epsilon close to rho in trace distance, meaning that this is smaller than epsilon. And okay, so just to give you a brief explanation on why the trace distance is useful and why it's important. It is basically the statement of the Euler-Wellstrom theorem, because this is just a side note to make you understand why we like trace distance. Is that because if you have, for example, one copy of an unknown quantum state, and this state is either, let's say, in rho or sigma, let's say you have a black box and you have the promise that in this black box there is either rho or sigma with probability 1/2, either rho or sigma with probability 1/2. Then if you want to discriminate between rho and sigma in this one copy black box scenario with like symmetric probability distribution, then the best probability of successfully discriminating the unknown quantum state. So let's write Psax as best. It can be like the best probability of successfully discriminating between rho and sigma by performing the most general measurements allowed by quantum mechanics. It can be written in this way, that in terms of the trace distance. So 1 plus 1/2 rho minus minus sigma. So you see that the trace distance really appears as in terms of the best successful probability of discriminating between two quantum states, between two hypotheses in the symmetric scenario. So this is why trace distance is important, because this has a strong operational meaning. It's and another reason is that in quantum mechanics, for example, you care about observables, expectation value of observables. So this is, let's say, reason one. Reason two is that if you have, let's say, an observable theta and you want to calculate the expectation value of a quantum state, you have trace of rho theta, but then you ask how much can differ this expectation value from expectation value of theta over the state sigma. And this via Holder inequality can be easily upper bounded in terms of the operator norm of theta times the trace norm between rho and sigma. So you see that if the trace distance is small, then also the expectation value um, of the two quantum states on a bounded observable are close to each other. So this is why this is the Holder inequality. So this is why trace distance is important because it does this operational meaning. Thanks. Okay. So okay. So let's still after this parenthesis, let's still come back to the problem of quantum state tomography. So so we understood that this condition formally can be written in this way. But this is not the only condition that we want to require. Indeed, the tomography algorithm, quantum algorithm, is inherently as a well, probabilistic outcomes. Rho tilde is a random variable. So when we want to make a statement on the output of let's say on a random variable, we cannot make statements like precise statements this way. We can instead require that the probability that this happen is large. So what we have to require, what we want to require is that the probability that Rho tilde is a good approximation happens is very close to 1. So is let's say larger than 1 minus delta. So delta here is considered to be is called the failure probability, while epsilon is the trace distance error. Both the trace distance error, epsilon, and delta are parameter of our problem. So we can fix from the beginning, and we can design our tomography algorithm to match these epsilon and delta guarantees. So by summarizing, the problem of tomography is that given an unknown quantum n copies of an unknown quantum state rho, we want to perform an arbitrary measurement, quantum measurement on it, and to retrieve after post-processing the outcome of this measurement, an estimate rho tilde that is epsilon close to rho in trace distance with probability of success that is larger than 1 minus delta. So both epsilon and delta has to be thought as a small parameter, basically. Okay. Now, another ingredient is that sometimes we have the assumption that our unknown state rho is not arbitrary, but is promised to be in a subset of states S. This subset of states, for example, could be the entire set of qubit mixed states, or the set of qubit pure states, or for example, the set of Gaussian states. So, okay, in general, so the tomography algorithm will be designed tailored to this set S. Okay, now let's define the important concept in quantum theory, that is the concept of sample complexity. Okay, so the sample complexity is the figure of merit that measures the quality of tomography. how how good you can perform the task of quantum state tomography. So let's fix this parameter epsilon delta in 0, 1, and let's also fix the subset of states S. And now let us consider. So let's define the sample complexity as a number that okay depends on the set S epsilon delta. It's just in N. It will be a function of all the parameters, such that basically I will tell you first in words. The sample complexity is the minimum number of copies of your unknown quantum state law in S that allows you to solve the problem of tomography with trace distance error epsilon and with failure probability delta. So the sample complexity N is the minimum say is the minimum N in N natural number such that um, such that given such that there exists a quantum algorithm so that um, the for given rho tensor n as input, it outputs. So given an arbitrary rho tensor n in input with rho in S, it outputs an estimator rho tilde such that rho tilde is epsilon close to rho with high probability, with probability larger than 1 minus delta. So basically, yeah, the sample complexity is really the minimum number of copies that allows you to solve the problem of tomography with error guaranteed epsilon and with failure probability delta. It will, of course, depend on the set S. Let's do some paradigmatic example. Let's consider the case of qubit mixed states. So in the case of qubit, where let's say the set S is the set of density matrices on an Hilbert space of dimension d, so over, let's say, CD. Okay, so this is the set of density matrices. In this case, the sample complexity, the asymptotic scaling of the sample complexity is given by b square over epsilon square. And then there is also a term that is like logarithm of 1 over delta. That is not really important for what I'm going to say. So the most important scaling is, okay, with this notation, I mean that this is the relevant scaling in the limit where b is large, epsilon is small, and delta is small. So the scaling with the dimension with the resistance error is like b square over epsilon square. And the scaling with the failure probability is always like log 1 over delta in quantum learning theory, because let's say if you can solve a problem with probability of success 2/3, for example, you can always repeat this um, algorithm, let's say log 1 over delta times, to boost the probability of success to be from 2/3 to 1 minus delta. So this is something that is called the boosting boosting algorithm, something like this. And it allows you to boost the probability of success to 1 minus delta, basically. So this is why when you read an application of quantum learning theory, sometimes you find that the statement is said like, okay, we can construct this quantum algorithm such that it succeeds with probability 2/3. This is not um, restrictive assumption, but this is quite general, and this is quite general because you can basically repeat the algorithm a few times to boost the probability of success. So from now on, I'll just not consider this parameter, this Fedor probability delta, because the scaling would be always like this. So in the qubit case, we said that this is our unknown result. Uh, there, it was proved in the something like 10 years ago, and yeah. So and the proof it's quite involved, and yeah, and but now it has recently um, simplified with this kind of random purification channel. Okay, this is another story. But I mean, I just want to say that even if this is the most basic example, the proof is not simple. Um so okay, so let's say a simple example. This is the case of the pure qubit states. So let's say that the set is now really the set of psi in CD such that psi is normalized. So in the case of qubit, the sample complexity reduces to d over epsilon square. So instead of d square, now there is d. And okay, so um, now now let's consider CV systems.
I have a
If you,
question.
yeah, sure.
So is this sample complexity allowing arbitrary entangled measurements?
Yes, that's true. That's a very good question. Indeed, there are, I mean, this is the simplest notion of the sample complexity that allows for any arbitrary quantum algorithm, so entangled measurement. There are there are also like other quantities, that other relevant quantities that one can study. For example, let's say the single copy sample complexity that allows the definition is this one, and um, the the quantum algorithm is restricted to just single copy measurements. So it cannot perform entangled measurement, but can perform just one measurement on each of the copy. So it gives you a row, you perform a measurement, you retrieve the outcome, then the machine gives you another state row, and you perform another measurement, and so on. And then after collecting all the outcomes, then you retrieve the estimate of your unknown quantum state. And the formula changes. So in this single copy scenario, it has been proved that if you restrict just to unentangled, this is with entangled measurement, with unentangled measurement, single copy measurement. So unentangled, I mean single copy. The sample complexity increases actually to d cube over epsilon square. So yeah, if you cannot perform, if you perform entangled measurement, you have an advantage in terms of sample complexity. Thanks for the question. So, okay.
Can I have a
Mhm.
question one more?
Sure.
It looks very obvious that in the sample complexity we ignore the inverse of log scale of delta. It looks very obvious. Is there any trial that to reduce this kind of sample complexity?
Sorry, I didn't understand the question. Sorry.
The,
Yeah.
and
Mhm.
you said that we will ignore boosting argument, the log of inverse delta, because it looks very obvious in this field. And
Mhm.
is there any trial that to reduce this scale of sample complexity? I'm trying to improve
Mm,
this.
Try to improve this. Okay. Okay. No, this scaling is actually like a necessary. And actually, okay, yeah, it's I'm just saying that what yeah, here what I want the message they want to deliver is that we are in these tomography applications. We are interested in the scaling with the dimension and the trace distance error. And I mean, the scaling with the failure probability is kind of less interesting because of this boosting argument. But I mean, okay, of course, one can keep the dependence on all the parameters. And what one usually does is to retrieve estimates from above and below, exact estimates of the sample complexity, and then just write the asymptotic formula and the asymptotic formula afterwards. So I mean, we will not. I mean, in calculation, we will not disregard, of course, the failure probability. We will keep in the calculations. I'm just saying that in this talk, I will not talk about the dependence of the failure probability because it will be always as log 1 over delta. So
Oh, sorry,
yeah.
one more simple question. Are we
Mhm.
considering the computational complexity of classical processing? Because
Okay.
yeah.
Mhm. Yeah, that's a good question. So the computational complexity is always larger than the sample complexity. And yes, one in general, one would like to have a quantum algorithm, a tomography algorithm that is not only sample efficient, so polynomial in the system size, but also time efficient. In this definition, we don't care about time complexity, but yeah, later on, yeah, it's an additional requirement. So yeah, that's it is interesting to understand also what is the time complexity. But in this definition, there is no notion of sample of time complexity. Yeah.
Okay, thank
Okay.
you.
Welcome. So let's talk about CV systems. So CV systems. Okay, I will just be very basic here, a bit informal. So um, in finite-dimensional systems, you have the concept of n qubits, for example. In CV systems, you have the concept of n modes. One mode is basically defined as one qubit with dimension equal to infinite. So it's basically an infinite dimensional qubit. The Hilbert space of one mode can be written in terms like of the span, of the vacuum, of the single photon state, 2, then D, and then so on until to infinity. These are called the Fock states. And so basically, the Hilbert space of one mode of continuous variable system is really all these Fock states from 0 to infinity. And when you talk about continuous variable system, usually you have multiple modes. You have n modes. So the Hilbert space will be, we are considering, will be H tensor n. And okay, so now we would like to understand what is, okay, so this is the definition of a continuous variable system. It's basically a quantum system associated with n modes, with this Hilbert space. And they represent, for example, bosonic systems, optical systems. So they are physically very much physically motivated. And what is the sample complexity of learning an unknown CV state? So since the dimension is infinite, we can just use these formulas, scales linearly with the dimension, and we quickly understand the sample complexity of learning an arbitrary continuous variable state is infinite. So without any assumption, the sample complexity is infinite because the dimension is infinite. Okay, but now we quickly realize that for a lot of physical purposes and many practical scenarios, we have we have an assumption on our state. We know that our unknown state has bounded energy. So we know that in a lot of physical scenario, let's say the energy of our unknown quantum state of light that we produce in our lab has energy bounded by a constant that you know, by a parameter that you know. For example, by the energy budget of the laboratory. You have a device that produces quantum states, and you know what is the power of this device, the energy power of this device. So this the unknown quantum state continuous variable systems in many practical purposes is not completely unknown, but it is promised to have energy that is smaller than a known parameter. You can think about the energy budget in your lab. Okay, let's define this formally. One can define the total photon number, and also the mean photon number. So you can write in Fock basis in this way. So it's basically diagonal in Fock basis with eigenvalue k. So it basically counts the number of photons that you have in your state. Okay, sometimes it's also written in terms of the so-called annihilation and operation creators in this way, a DAG array. Or yeah, sometimes also proportional to x squared plus p squared, where x and p are positional momentum operators. It's not really important now. But what I would like to say is that, so this is called the photon number operator of a single mode. And for example, let's consider, yeah, now we are considering just the case of one mode system, single mode. This is the photon number operator. And the requirement that we have on our unknown quantum state is that the expectation value of a trace of rho n, so the mean value of the photon number is smaller than a parameter E. And this is the energy budget that you have in the laboratory, or the energy of the light source, the energy power of the light source that produces rho. So basically, we want to learn an unknown state, rho, that is promised to be in this class of states. So say rho that is in the Hilbert space of one mode, subject to trace of rho n is smaller than E. So this is actually a set that depends on the parameter E. And now the question, now it's interesting to ask what is the sample complexity of learning quantum states of continuous variable systems with an energy constraint. And this is not anymore infinite. And we can actually calculate what is this sample complexity. So I will just talk about single mode now, just for simplicity. The problem is already interesting for single mode systems. Then one can generalize. I just want to deliver the basic idea. This is like I think the simplest calculation in this analysis. I want just to do one proof in this talk, and this is that will be this one. So a simple upper bound on the sample complexity of learning energy constraint states. So so intuitively, fixed E, for example, let's consider, for example, if E is equal to 1, rho cannot, when you write rho as in terms of, let's say, for example, some constant, then 0, 0, plus, if you have a term like Cn, N, for example, in this in the expansion in focal basis of rho, this term cannot be very large if n is large, because you have this energy constraint. So basically, all these coefficients are suppressed. This is the rough intuition. So let's make this intuition rigorous. So we want to say that basically we can truncate the state rho in a finite-dimensional Hilbert space by making at most epsilon error in trace distance. Okay, so basically now let's recall a very useful lemma in quantum information theory that is called gentle measurement. Gentle measurement lemma. This is to make this intuition formal. So the gentle measurement lemma tells you that if you have a projector pi, this is a projector, and then you have a quantum state rho, then it holds that the trace distance between rho and its projected version is smaller than the square root of the trace of the complementary projector times rho. Okay, so what is the meaning of the gentle measurement lemma? The gentle measurement lemma tells you basically that if you have a projective measurement, let's say pi and 1 minus pi with outcome P of m, and you know that this outcome is very likely to happen, then the post-outcome state after this outcome happens, that is this one, will be close to the initial state, would be very close to the initial state. This is because if I mean, let's say if trace of pi rho is very high, so the probability that this outcome happens is high. So it means that let's say that is 1 minus epsilon. Then this quantity will be epsilon. So basically, it means that the post-outcome state is epsilon is square root epsilon close to the initial state. So gentle means really that you are performing like a measurement that does not perturb your state too much, because you already know that the outcome is very likely to happen. It's just a quantitative estimate based on this intuition. But now, how can we use this gentle measurement lemma for this purpose? The gentle measurement lemma can be used in this way. So let's define the projector of pi m on the first m Fock states. Okay, so this is the projector of pi m, and so let's take a state rho in the set SE. So it's a state rho such that the trace of rho n is smaller or equal to 2e. This can also be written in Fock basis as k0 infinity, k, rho, k. Okay, so this condition basically can be written in this way. So this is smaller than e. We have these guarantees. Okay, let's apply the general measurement lemma with this projector. It depends on m. Okay, so we can write this in this way. So we can expand this 1 minus pi m. We can write this as k m plus 1 infinity k rho k. But now you can put here a number that is always larger than 1, so that we can employ the inequality, and we take this number to be k over m plus 1. Since this sum is since m plus 1, okay, actually also km. So this is an inequality because this number is always larger than 1 because of this condition. So then we can actually restrict this sum to hold everywhere from k equals to 0. And now we exploit this equation here, and we can write that this is exactly square root of trace of rho at over e. Sorry, over m. And by assumption, this is an energy constraint state, so it's smaller than e over m. Okay, so we want to make m large enough so that this state, the projected state, is close in trace distance to our initial state, because we want basically to approximate the infinite dimensional state with a finite dimensional state, because now this state here is not anymore the infinite dimensional, but it's basically supported on the first m Fock states. Okay, so basically this is why we are doing this, because we want to recover the finite dimensional case, and so basically we want to require that this is smaller than epsilon. And in order to require this, so it suffices to take m that is larger than e over epsilon square. So we can actually choose m to be the integer part over e over epsilon square. So basically, this says that if you take m in this way, then let's say that if you perform this true outcome P of m on your unknown quantum state rho, then if this outcome happens, the state is projected in this finite-dimensional Hilbert space of dimension m, and this is you are doing this without modifying your state too much. So it's still epsilon closing trace distance. So basically, the algorithm that we can consider is just that. Okay, you have your n copies of your unknown quantum state. You perform this true outcome P of m on each of the copies. And if you have the outcome by m, then okay, you keep the state. Otherwise, if you have this outcome, you just discard that copy. So basically, by doing this process, and in this process, will you lose a few copies with high probability because the measurement is likely to happen. So basically, you reduce your multiple copies to, let's say, many copies of the projected state. So with this process, you can reduce the problem by using rho to pi m rho pi m over trace of pi m rho. But now this is a density matrix over C to M, basically. So now you have many copies of this state here, and you can perform finite-dimensional tomography on this finite-dimensional state. And we know that the sample complexity of finite-dimensional tomography is. So the sample complexity, for example, in the mixed state scenario, it will be order of m square over epsilon square. Substituting what is m here, we have that this is so e square over epsilon 6 in the mixed state scenario. If you have the assumption that your state is pure, you have that this is reduced to m over epsilon. This is order of e over epsilon fourth. This is the pure state scenario. Okay, so basically, the reasoning is that okay, an energy constant state is basically a finite dimensional state on a bigger Hilbert space, so we can just perform finite dimensional tomography there, and this provides the upper bound on the sample complexity. How to find the lower bounds on the sample complexity? So the lower bounds, okay, I will just give you the rough idea, and this is not, I mean, this is like the basic idea to find lower bounds in quantum learning theory. And the reasoning goes from the so-called Olevo theorem. So basically, let's say that you have your set of quantum state S. So this was the like for upper bound. Now I will talk to lower bound. So let's say that you have your set S, and you can come up with a construction of states that are a lot of states in this set that let's say you can construct m states in this set, and each of these states are let's say far apart at least 2 epsilon between each other. So that if you have an unknown state between these m many states, you can run if you have like many copies of these states, you can run your tomography algorithm, and you can distinguish which state it is between this family with high probability. So what is the argument to find lower bounds? So let's consider this communication protocol. So Alice choose a message between I, a message I between 1 and m, randomly, uniformly at random, let's say. And this message I is encoded in one of these states. So these states are indexed by an indexer 1 or 2 or 3. They are indexed, and there are m of them. So let's say that Alice pick I in 1m and produces, she does this communication protocol. She produces rho I tensor n, where n is the number of copies, basically. And then she sends this quantum state to Bob. And Bob wants to recover the message of Alice, wants to learn what I is. And if there exists a quantum algorithm, a quantum tomography algorithm, then Bob can just run this protocol. And since these states are 2 epsilon far apart, and the tomography algorithm works with precision epsilon, Bob can just discriminate between these hypotheses and output I with high probability. So basically, via this protocol, Alice and Bob are able to communicate M messages. So that log 2m bits. And they are doing this by transmitting the quantum states. But it's a basic notion of quantum mechanics, known as Olevo theorem, that if you transmit 1 qubit, for example, you cannot transmit more than 1 bit of information. So by sending m qubits, you can transmit at most m bits of information. So basically, this since these are quantum systems, they cannot m cannot be very large. This puts a constraint on m and on n. This is the idea how one can find a lower bound on this n. So, for example, in the case of let's say n qubit, let's say the case of n. So let's see the case of qubit. Qubit of dimension d. This becomes basically that log 2m, that is the number of states that are 2 epsilon far apart in this set that you construct. So your goal here, when you want to find the sample complexity lower bound, is to construct as many states as you want in this set. We want to construct a large family of states that are in this set and are 2 epsilon far apart. The condition is that the number of bits is smaller than the logarithm of the dimension of the Hilbert space. And the dimension of the Hilbert space here, you have n copies of a qubit. So let's say hd to tensor n. It's just log 2d to the power of n. So it's just n log 2d. So basically, here this implies that n has to be necessarily larger than log 2m over log 2d. So basically, if you find a large family of states, then let's say let's say that is like exp of for example b square in the mixed state scenario, you find that actually this is order d square. So this is the idea. So basically, you construct many states in this epsilon net, and then you have a lower bound of this form. Okay, this is just a rough reasoning. Then it made formal by like then the Levaux theorem can be made formal in terms of mutual information, accessible information, like and then Fanonian inequality. But this is like just the basic reasoning to find the lower bound on the sample complexity. If there exists a tomography algorithm, then and the sample complexity has to satisfy this formula. So you just down. So the problem is just reduced to find a large set of states that are in this set, and they are epsilon, 2 epsilon far apart. So this is the basic idea to find the lower bounds on the sample complexity of tomography. In the continuous variable setting, there is the technical difficulty that this is not the dimension is infinite, so you cannot apply this version of the Levaux theorem, but you can still make refined reasonings when you have when you talk about the statement of the Levaux-Wellstrom theorem in terms of mutual information. If you have an energy constraints, basically the mutual information in this communication scenario cannot be, it's not infinite, but is bounded. So, okay. So basically, okay. Well, I'll just tell you what is the result for n modes. The reasoning is the reasoning that we have in the paper follows this kind of general reasonings. So for n modes, basically, okay, you can define still the energy constraint. You can define the total photon number as the sum between J1 of and J, where this is the photon number of the mod J. And the energy constraint that you can pick is of the form that your n mode state satisfy the condition that n tot is smaller than. Okay, here we pick like n times c. This is because this is an extensive quantity, so it makes sense to require an energy constraint of this form because you don't want any implicit dependence on the energy. So this E now is like can be taught as the energy per mode, basically. Okay. So the sample complexity that for pure state tomography, continuous variable states, turns out to be okay. Here I'm being informal because I'm removing some dependence on like some dependence on epsilon and on the base of the exponent. It's like epsilon n to the power of epsilon 2n. Okay, this is the sample complexity of pure state. Okay, here I'm putting a tilde because I'm not considering here there should be something like 1 plus something like this. So it's not really tight, this bounds, but it is tight up to this correction. So this is why I'm putting the tilde here. But basically, the relevant scaling in the limit has this dependence. It scales exponentially with the base of the energy, and then it scales has also dependence of this form. And yeah, here I'm just saying this is the relevant scaling when all the parameters are like the energy is large and is large, epsilon is small, and but yeah, it's an informal writing, this one. So But what one realize is that while in the finite-dimensional setting, the sample complexity scales as 1 over epsilon squared. Here in the continuous variable setting, it scales as 1 over epsilon to the power of 2n. This is a much more unfavorable scaling, because let's say if you want to decrease your error between epsilon and of a factor of 2, then here in the finite-dimensional setting, you just need to increase your number of copies from n to 4n. While in the CV setting, you need to enlarge your number of copies to 4n. So this is an arresting behavior. This is why we say that tomography of continuous variable systems is extremely inefficient, even though of energy constraints. And so basically, tomography of energy constraint states is extremely inefficient, much more so than tomography of qubits. Okay, now I don't have so much time left. I will just briefly go into the topic, last topic of this lecture, and this is the topic of Gaussian states. So, sorry, Junseo, how much
Yeah.
time do I have?
Sorry?
How much time is it left?
Maybe you can do more about 15 minutes or
Okay, great. Yes, I will just give you the brief explanation. So, do you have any questions until now? Okay,
I have a
great.
short question.
Mhm.
A very short question. About your example about one modes, you said that the pure complexity becomes E over epsilon to the 4, maybe.
Mhm.
But in your N mode complexity that you stated, it becomes E over epsilon to the square. I'm curious
Yes,
about
That's
yeah,
that's a very good question.
where's yeah.
So you are saying that in this formula there is E over epsilon fourth. Okay, this is
Yeah.
exact. Yeah, that's completely okay, this is true. But the answer to your question is it is in this tilde. Here I'm not. I should write also times epsilon square here. Then I'm just deleting this term here because this is an informal writing. In the paper we have explicit expressions, but in the presentation of this result, just to tell what is the physical implications, we write in this way, just to not. Just to deliver the message that the scaling with the number of modes it's like this. But yeah, the formula in general of the sample complexity is very much complicated. Can be upper bounded in terms of an explicit dependence on n, epsilon, e, and lower bounded also in terms of an explicit dependence over all the parameters. This is just like really a rough. This is like a simplification of the formula, but you should not take this as statements, just more like I want to communicate to you what the formula looks like. But in general, it's more complicated, and there is a mismatch between the upper bound and the lower bound. And this mismatch, for example, it's exactly given by this epsilon square that there is here. This is present in the upper bound, but not present in the lower bound, and also in terms of the constant that appears here. The relevant scaling with the number of modes is this one. Yeah.
Okay, thank you.
You're welcome. Okay, so by summarizing, we're seeing that tomography of energy constrained states is extremely inefficient in terms of sample resources, and also in terms of time resources. But it's also known that for a lot of practical implications, we have the assumption that our bosonic quantum states is so-called Gaussian. Gaussian states are ubiquitous in quantum physics, in experiments, and in nature. And they have a lot of structures, a lot of structure. And if you know that a state is Gaussian, it's a really particular class of continuous variable states. So it's interesting to ask the question, what is the sample complexity of tomography of Gaussian states? So in this part, in this last part of the lecture, I will just briefly mention some results in this topic. So what is okay, first, what is the Gaussian state? Gaussian state is basically a Gibbs state of a quadratic Hamiltonian in the, let's say, annihilation and creation operators, or position and momentum operator. And the quadratic Hamiltonians are like important in physics. They're like what's called free Hamiltonians. And so Gaussian states, you can define it as either ground states or Gibbs states of quadratic Hamiltonians. And what is important for the for what I'm going to tell you is that a Gaussian state rho can be uniquely defined in terms of the so-called first moment and covariance metrics. The first moment is if this is a state of n modes. This is just a Chuan real vector, and this is a covariance matrix. It's just a Chuan times Chuan real matrix. So Gaussian states are uniquely identified by these parameters. And these are just, let's say, 4n square parameters, and these are just 2n parameters. So you have to learn these parameters. There is a one-to-one correspondence between the set of Gaussian states and the set of first moments and covariance matrices. And this is actually what happens for Gaussian probability distribution. When you talk about a Gaussian probability distribution, it is uniquely identified by the mean and the covariance matrix. This is actually the same in Bosonic systems. And you can write the first moment the covariance matrix in terms of expectation values of position and momentum observables, annihilation operators. So quantities that can be estimated via quantum measurements. So I'm just telling you that you can actually, given your copies of your known quantum state, you can estimate your first moment and covariance matrix with arbitrary good precision via quantum measurements. So basically, and if the state is Gaussian, you can actually exploit the structure of the Gaussian states to make this estimation of first moment covariance matrix also quite efficient. So basically, what one can have is that a statement of the form that if the number of copies n is large enough, we can produce an estimator, let's say, of a covariance matrix B tilde, such that it's epsilon close to rho in some norm. Say, I will not specify the norm. I will just say that we can make a statement of this way, like the probability that the estimator of the covariance matrix is epsilon closed is large, for example. So we can make statement of these guarantees on the estimation of the covariance matrix first moment. These measurements are called, to estimate the first moment covariance matrix, are called sometimes heterodyne detection. But what we care in tomography is the trace distance error. We don't want this, but we want this condition. So basically, what ones want is that let's say that you have your tomography algorithm, you estimate M tilde and V tilde, and then you want to associate with this estimator the Gaussian state that is associated with these estimators, and you would like that this is close to the true unknown Gaussian state with precision epsilon. And in order to make this analysis, we need bounds on trace distance between Gaussian states. So let's consider the case of first moment 0. We would like to have, so this is the Gaussian state with covariance matrix V and the Gaussian state with covariance matrix W. We would like to have a way to propagate the error from the estimation of the covariance matrix to the trace distance error. So some deriving bounds on this trace distance is necessary, and it's quite turns out to be quite hard to do that. And after to work, one can actually show that this is can be bounded in this way. Something like if I remember correctly, something like this. So basically, if you estimate your covariance matrix sufficiently well so that this is, let's say, very small, then this is small. So via this inequality, you can perform actually a sample complexity analysis of tomography of Gaussian states and derive sample complexity guarantees on the problem of tomography. And for example, if one performs this heterodyne detection, that means just taking your n copies of your quantum state and doing this estimation of the covariance matrix in first moment, then propagate the error. One finds a sample complexity that scales basically as n cubed over epsilon square, and then there is the energy. So in the same notation as before, where the trace of rho and tot is smaller than ne using this notation. So basically, what one finds is that the sample complexity of tomography of Gaussian states scales now only polynomially in the number of nodes and in the energy. So tomography of Gaussian states is efficient. We don't have any more an exponential dependence, but only a polynomial dependence. And also the time complexity, the time of this algorithm is scales polynomially. So that's so basically this shows that tomography of Gaussian states is efficient, while tomography of energy constrained states is very inefficient. And okay, just the last comment is that so okay, this heterodyne tomography is what experimentalists do in lab usually. Take your light source and do this kind of beam splitters and the homodyne detection to estimate the covariance matrix in the first moment of the unknown state. And actually, the sample complexity of this algorithm is given by this formula. So it's natural to ask, can one do better than this? Actually, the answer is yes, one can do much better than this. The trivial protocol of like estimating the first moment of the covariance matrix is not the best one. There exists another protocol we did follow-up work that we can call like adaptive unsqueezing protocol. That basically it's an adaptive protocol that progressively unsqueeze the unknown quantum state. Once that the squeezing, okay, I'm not going to define the squeezing right now, but once the squeezing is sufficiently small, then at that point you can perform heterodyne detection. And actually, this protocol has a sample complexity of n cube over epsilon square, so this is same scaling, but it has a dependence on the energy, this roughly speaking log E. So a double logarithmic dependence on the energy. This is really a mild scaling on the energy. If even if scale like a joke, even if the energy is the energy of the entire universe, then log E would be really still quite small. Like if E is like 10 to 300, then log E would be still of um, quite small, 10. Okay, so basically, yeah, this is a great improvement. This is why we say that tomography of Gaussian states is basically energy independent, because it actually allows you to learn to have like rigorous estimations of the Gaussian state with like very like even if the state is highly uh, energetic or highly squeezed, you can learn it with a few copies. And yeah, so this is really a property of Gaussian states, and it cannot happen if the state you don't have the Gaussianity assumption. Okay, so there are a lot of open problems in this direction. For example, what about lower bounds? Uh, and what is the optimal protocol? Is this really the optimal protocol? If this is currently known, I mean, today, maybe in 1 or 2 months, yes, today. Okay, but I mean, this is a really active field of research that I I'm exploring in my PhD, and also a lot of collaborators are exploring right now. And this is not the end of the story. There will be development soon on this topic. And yeah, um, so if you have questions or curiosity, or if you would like to chat about more about open problems, yeah, please ask questions or text me via mail, and I'm happy to discuss.
Yeah, thank you very much for a nice lecture today, Francisco. And is there any questions from students?
Okay, I have a question. So you said Gaussian states are efficiently like we can do efficient tomography for Gaussian states. I guess it's like kind of similar to the Gauss-Menier theorem for Clifford circuits for qubit systems. Like, are they actually kind of connected, or actually are like they're just like not related to each other?
Okay, so yeah, so you're referring to the classical simulability. If there is a connection between the like efficiency in classically simulating a Gaussian state or a Clifford state, a stabilizer state with sample complexity of learning. Is that the question?
Yeah, that would be the
Okay.
question.
And, as far as I know, there is not direct connection between classical simulability and learning. Yeah, but this is an interesting question. I mean, yeah, all these states, Gaussian states, are efficiently can be efficiently simulated as a Clifford circuits. Yeah, that's true.
I have another question. In your explanation, you used the QD tomography of complexity d to the square over epsilon to the square. And in my knowledge, if you know a state that has a rank R, you can perform the tomography as dr.
Yes,
And
that's true.
can we use that protocol to enhance or make it more efficiently to use it in a CV tomography setting?
Yeah, that's a great question. This is actually true. We can do that, and you can. Okay, so basically, above with the gentle measurement lemma, we showed that basically the effective dimension of a quantum state of a like quantum state energy constraint of the CCV system is E over epsilon square.
Yes.
One can define also a notion of rank, like one can define something like this, an effective rank, and yeah, one can find like something like square root of these. Yeah, I think that it's something like, if I remember correctly, it's like something like square root of a square. Yeah, I don't want to write it, but I mean there is something like this. Yeah, and
Yes.
actually, um, yeah, one can do that, and can improve the sample complexity of tomography of a mixed state by saying that the sample complexity of CV systems is the efficient and the effective over epsilon square, as you exactly pointed out. Yes, that's true.
Thank you.
Okay. Just a spoiler what my Antonio Mele will talk about in the next lectures. Antonio is my brother. He will talk about. So we saw that continuous variable system is of like non-Gaussian systems are extremely inefficient to learn. But then we show that Gaussian systems are very efficiently to learn. So this is not. So he will talk about this transition. I mean, there is like a whole degree here to go from Gaussian states to arbitrary non-Gaussian states. And in the middle here, there is the so-called concept of p-dot Gaussian states, and that analyze this regime to go from the Gaussian setting to the non-Gaussian setting. So this will be seen in the next episode. Okay.
Yeah, I have very simple, funny question. So, who
Sure.
is older brother? You and Anthony.
Sorry,
Yeah, who is older
can you
brother?
repeat? Antonio of Shoe
I
Minutes.
see. I didn't know that. Okay.
Okay.
Is there any
So
more
thank
questions?
you.
No more questions from students? Okay, then we can finish today's lecture. And thank you very much for
Okay.
today's lecture, Francisco. And see you
Yeah.
next week.
Thank you. Thank you so much. And so see you next week. See you.
Bye bye.
Bye.